Okay, welcome to the next class. So, we were telling about we want to calculate the slip at which maximum torque occurs. Of course, this can be done by differentiating this and get it, but because we have already developed the equivalent circuit, it can be done in a much more simpler way instead of trying to differentiate it and set it to 0, get the value of alpha. So, I refer to this equivalent circuit, but since I am writing R Thevenin's X Thevenin's, of course, this thing is not there by mistake I wrote JXM. So, it is a simple series circuit. So, I will better redraw it here. So, the Thevenin's equivalent circuit is now R Thevenin's X Thevenin's, and there will be no X M because already Thevenin's equivalent between these two circuits I have found out. This is V 1 and this is X 2 dashed and this is R 2 dashed by S. So, you want to maximize the torque, and what is the torque? You recall I told you that the power in this resistance is PAG, and PAG is also a measure of torque, because PAG by some constant number 2 pi n s gives you torque in Newton meter, or PAG itself in synchronous watt gives you the electromagnetic torque developed by the machine. Therefore, if you look at this equivalent circuit in which I am varying S here. So, torque will be maximum, T E will be maximum when PAG is maximum. If air gap power is maximum, at what slip, if I can calculate that, then torque will be also maximum, because torque is nothing but PAG, that is the whole idea. Therefore, in this circuit, it is now a circuit problem. There is a circuit, forget about motor, there is a variable resistance here. Why it is variable? Because S will be changing. I want to find out at which S T is maximum. Therefore, I want to maximize the power in this resistance. So, why not apply maximum power transfer theorem, which we have already learned, and do not try to just differentiate this expression of torque, not like this way we will not do. So, T E will be maximum when PAG will be maximum, that is at what slip power is maximum in this resistance R 2 dashed by S. That is what you have to find out, and we know it is an AC supply. So, all the impedances looking from this can be considered to be the impedance of the source along with V 1. V 1 is the source as if it is the internal impedance, and here is a variable resistance, and power is maximum when R 2 dashed by S, this value of the resistance is equal to the magnitude of the impedance of this internal impedance of the source, that is it must be equal to this R Thevenin's plus R 2 dashed by S it will be equal to square root of R Thevenin squared plus X Thevenin's plus X 2 dashed whole square. It is at that value of slip torque will be maximum. That is this is equal to nothing but R2 dashed by alpha. I am interested to know what is the value of alpha. Anyway, we put it like this. If this is the case, then this is the slip at which maximum torque will occur will be alpha is equal to R2 dashed under root this one. This is the result. In one stroke we get this result, no differentiation. So, at this value of slip maximum torque will occur. Then the next question was, then what is the value of this maximum torque? T max, T e, general expression of T e is equal to, many a times I have written, it is nice to write over and over again, so that it comes to, we easily can write it. So, this is equal to this was for any value of slip R2 dashed by S, this is R Thevenin's plus R2 dashed by S whole square plus X Thevenin's plus X2 dashed whole square. This was the general expression of that. Now, if you want to calculate T max, to get T max, put R2 dashed by S, because S comes along with R2 dashed. So, R2 dashed, put R2 dashed by S to be equal to this thing. Put this above in the above equation, and then your T e max will be equal to 3 V Thevenin squared by 2 pi n s, it is there. Then on the top this one is nothing but this. So, put that plus X2 dashed whole square divided by R Thevenin's plus this R2 dashed by S, put once again the same thing, plus of X Thevenin's plus X2 dashed whole square. This will be the value of T max. No, this is squared. So, this will be the value of T max. Now, it looks quite, do not try to memorize this because no point, but only thing is this can be further simplified in a nice form. For example, you expand the numerator, then what will happen? There will be R Thevenin square plus X Thevenin square, A plus B whole square, like that, and also here will be another X Thevenin square coming, is not? It will be like that, you just expand it, and here it was correct, na, everything. So, this is equal to 3 V Thevenin square by 2 pi n s into, so it will be R Thevenin square, let me write A square plus B square here, here it should be R Thevenins. No? Please note that this is R Thevenins. By mistake I wrote. So, this is R Thevenins. So, if you remove this, so A square plus B square will give you 2 R Thevenin square plus x Thevenin plus x 2 dash squared. So, this is A square plus B square plus 2 A B term. It is some routine, I mean simplification, algebraic manipulation, nothing great work, but anyway let us do it in longhand. So, 2 A B term plus x Thevenins plus x 2 dash whole square. So, what I will do it, I will write it, there was one x Thevenins plus x 2 dash whole square coming from here and there was already there, and on the top it is 1. No 1, it is under root this one, R Thevenin square plus x Thevenins plus x 2 dash whole square. Now, what we will be doing is very straight. Now, I know what to do. So, T E max, maximum value of the electromagnetic torque will be 3 B Thevenin squared by 2 pi n s, and you see there is a 2 you can take common. Okay. So, that it will become 4. I will write it like this 2 and this 2 pi n s, and then okay, let me this step let me write. So, that so on the numerator it will be R Thevenin squared plus x Thevenins plus x 2 dash squared divided by this is R Thevenin squared plus these 2 I have taken outside. So, x Thevenins plus x 2 dash squared plus R Thevenins square root of R Thevenin squared plus x Thevenins plus x 2 dash squared. It will be like this, and you know the next step is obvious, that is this 4 pi n s is there. What you do? You bring this numerator term below, okay? Divide both numerator and denominator by this. So, that it will become 1 here, and here it will become, if you divide bring this down, it will be R Thevenins from this, and it will be R Thevenin squared plus x Thevenins plus x 2 dash squared, that is all. No further simplification is possible. This will be this. So, bring this down. Okay. So, this will yield when you divide this term, and this cancels out and R Thevenin. So, this is the expression of the T E max. Okay. You must agree with me, if x m is also neglected in the equivalent circuit, if you neglect x m, then R Thevenins and x Thevenins will be simply R 1 and x 1. If x m not neglected, if x m is high, very high, is high, so that in the equivalent circuit x m come in parallel, this x m then can be treated as open circuit, and then of course, your V Thevenins will be equal to V 1, your R Thevenins will be equal to R 1 and x 1, and it is already in that Thevenin's equivalent form. source with its internal resistance if x m is very large compared to this R 1 x 1 this series things. It is obvious. So, if x m is high, then you know V Thevenin's will be equal to V 1 and R Thevenin's is nothing but R 1 and X Thevenin's is X 1. You just remember that so that you can calculate the electromagnetic torque very efficiently. So, two things we have got. One is the value of the slip at which maximum torque occurs, that is alpha, and that value was equal to, I wrote earlier, that value was equal to 1 over square root of R Thevenin squared plus X Thevenin plus x 2 dash squared. This is the slip at which maximum torque occurs and this is the value of electromagnetic torque. So, these are the two most important formula of a 3-phase induction motor. The problems are like this, that all equivalent circuit parameters are known, then sketch the torque slip characteristics, take some typical values of slip, and in today's in terms of today's way of calculating, you can write a small program. Okay, slip changes from 0 to 1, calculate T from these two expressions, sketch it, and then you can also calculate T max, and the slip at which T max occurs means this is the torque slip characteristics. I told you it was like this. This is S equal to 1, this is S equal to 0, and this is the slip at which maximum torque occurs, and this is T E max, and this of course is the starting torque, T starting. Got the point? This is 0, and if you have drawn like this, then speed is doing this. This is n r equal to 0, I am sorry. This is n r equal to 0 and this is n r equal to n s. Okay. So, for a well designed machine, what I was telling, alpha is of the order of 0.1 or so, and this is the torque slip characteristics. Now, the important things about torque slip characteristics is that you note that the value of the slip at which maximum torque occurs and the value of the maximum torque, these two things, these two are independent of the value of S. These two quantities independent of R 2 or R 2 dashed. R 2 and R 2 dashed are one and the same thing, reflected value. Therefore, T maximum and alpha, the slip at which maximum torque occurs, are independent of the value of alpha. Okay. Acha, we will come to this slightly later, but let us now try to understand what is going to happen to this torque slip characteristics if rotor resistance is increased. For example, I have told you this is your stator which you are energizing, and this is your rotor which also houses a 3-phase winding. And I showed it to be shorted, that is fine, and the torque slip characteristics we now have a fair idea, and this torque slip characteristics was like this. This is slip to 1. Now, and this is T max. The machine in any case can produce this much of maximum electromagnetic torque. Opposing torque you do not know. Okay? It has nothing to do with the load torque, it is machine's capability. If it runs at this slip, it will develop this much of torque. Therefore, your load torque must match that at that point, that is the thing. Now, this is the alpha whose value is about 0.1. Okay. Achha, now, let us do this small thing to understand, to use these torque slip characteristics to understand many interesting thing of the induction motor. This is T. For example, suppose on the shaft of the machine there is a small frictional torque present. Okay. This is T friction. This line, okay, is T friction. Then what is going to happen when you switch on the supply? At that time slip was 1 and we say that this is the starting torque and opposing torque is this much. So, T starting is greater than T friction. So, machine will accelerate, and also do not forget that this side is speed. Always draw these two things to avoid any confusion. This is n r equal to 0 and this is n r equal to n s. So, the motor will accelerate because on the motor two things are acting, one is T electromagnetic, another is a constant value of T friction, and therefore, machine will start accelerating. In which direction? Because T is greater than T friction. So, it will start increasing its speed in the clockwise direction itself. Direction of electromagnetic torque decides the direction of rotation when the machine is operating as a motor. Therefore, speed will rise. Speed is this. So, operating point it was here, then it will move because slip is increasing. At this point what is happening? When it reaches this much of speed, electromagnetic torque is still greater than T friction, it will accelerate. Here also any value of speed you take, machine goes on accelerating. Of course, rate of acceleration depends upon the difference of these two torques, but nonetheless, so long T is greater than T friction, machine will go on accelerating, and eventually it will come here also. Then the difference of torque is the highest, the rate at which its speed is increasing, it will become much more. In fact, if you do some experiments on induction motor on no load it is, and you have switched on the supply, you will find okay, machine is accelerating, then suddenly it is accelerating very fast. Perhaps it is crossing this zone at that time. But nonetheless, T max is greater than T friction, it will accelerate and operating point will shift, and in this way it will come here when the electromagnetic torque developed by the machine will be equal to the opposing T frictional torque, and machine will settle there. Therefore, it will run at a speed very close to synchronous speed. This is ns in terms of speed. The operating point will be this one. It has to develop certain amount of electromagnetic torque, which will match the friction, and yes, the machine is capable of doing that, and it is here it does so. Therefore, at no load, no load means only opposing torque is frictional torque. At no load, speed motor will settle down, to a speed called NR0, no load speed, NR no load. This point is NR0 to a speed NR0, where these two torque balances, and this NR is less than but very close to NS. That is what I want to tell. Why it is very close to NS? Because T friction itself is small and machine will settle down there. Suppose to give you some example in terms of numbers, suppose it is a 4-pole machine and supply frequency is 50 hertz, then synchronous speed is 1500 rpm. Then what I am telling, NR will be very close to 1500, depending upon, of course, actually how much is the frictional torque, which is very little. Whoever has designed the machine, bearing this that, he must have taken that into account, and NR may be say 1490 rpm. So, it will be the operating point under no load will be very close to the synchronous speed ns, but less than that. Had there been no friction at all, then machine would have accelerated, then this line is not there and it will come here. When the opposing torque is 0, electromagnetic torque developed by the machine is 0, and machine will settle down to synchronous speed. Anyway, that is a very ideal situation. That is why we tell the sleep of the machine can vary from 0 to 1 for motoring mode, and synchronous speed that it will run is not a practical proposition, because there will be always some, however small it is, some frictional torque will be there, and the intersection of this opposing torque and this torque slip characteristics will determine the operating point under no load condition. So, this is no load. We will discuss further, because this torque slip characteristics, as I told you, can help me to understand many other finer points of a 3-phase induction motors. Thank you.